In the attenuated total reflectance Fourier transform infrared experiment, or ATR FTIR, you're going to be measuring the concentration of ethanol in various solutions. Okay? And we're going to do so in percent. Okay, so percent ethanol in various solutions. IR, infrared spectroscopy, is a type of vibrational spectroscopy. So when we think about this, we need to imagine the molecule in its ground state. And when we shine infrared light on that molecule, it raises that molecule up to a different vibrational level within the ground state. And that's represented here. So S0 is our ground state, V1, V2, V3, and so on up to Vn are the different vibrational levels in that ground state. And when we shine different wavelengths or frequencies of infrared light onto our molecule, it goes to these different vibrational levels. These vibrational levels will correspond to bands in the infrared spectrum. Okay? When we measure our infrared spectrum, our y-axis is going to be typically in percent transmission. Okay, but it can also be in absorbance. Okay, it is an absorption. And our x-axis is going to be in wave numbers, which is given in inverse centimeters. Okay. So when we look at the infrared spectrum of ethanol, it has a number of different features that we're interested in. It's going to have, if we draw the structure, okay, we have methyl group, or ethyl group, excuse me, and hydroxyl group. So we're going to have an OH stretch that's going to show up in our infrared spectrum. This OH stretch has a very strong broad absorbance. Okay, it's going to show up a lot. One of the problems with simple in quotes, Fourier transform infrared spectroscopy is that water, which has OH stretches, absorbs very strongly. So much so that it's nearly impossible using transmission FTIR to obtain an infrared spectrum in aqueous solutions. So that's where this ATR comes in. Okay? What ATR is a crystal upon which we'll put our sample, ethanol, in aqueous solution. And what happens is we shine IR light through the crystal, and just a small amount of that IR light is absorbed at the interface of the sample and the crystal, and it gets reflected, and we can imagine we're getting just small absorptions each time that light is reflected back down to the crystal. Okay, eventually the light goes to a detector where we can determine what amount of light and what wavelengths or what frequencies that light was absorbed. The nice thing about ATR as opposed to transmission IR is that it has really, really short path lengths. Like really short path lengths, okay? The depth of penetration into the water or the aqueous solution is so small, okay, that we can use aqueous solutions because the water isn't overcoming the rest of the important part of the spectrum. Okay? So that's what's really cool about ATR FTIR. The other thing that's really cool is that it's super easy to use. Right? Your TA will explain the instrument to you and show you a few things. There's also a guide. Really the hardest part is manipulating the software. But let's go back to our ethanol. So we're going to have an OH stretch. And this is going to occur somewhere between 3,500 and 3,200 wave numbers. Okay. We're going to have a CH stretch. And this is between 3,000 and 2,900 wave numbers. And we're going to have CO stretches. And this is between 1,260 and 1,050 wave numbers. Now, if we think about an aqueous solution of ethanol, we can't monitor OH. And the reason is that we're in water, okay? Aqueous. So there's going to be tons of OH. And the stretch is not going to be dependent on the concentration of ethanol. The thing that's most going to be dependent on the concentration of ethanol is this CO stretch. Okay? So these are the bands that we're going to monitor. Make sure you know exactly where in the spectrum the CO stretch is going to occur, because we're going to measure the area and the height of the bands present in the CO stretch. Okay, stretching region. So what other things you're going to do? You're going to have, you need to make 6 solutions with known concentrations, and you're going to be given 95% ethanol to do so. And keep your concentrations in percent. So it's going to make your life easier. For a few of the samples that have percent ethanol reported, obviously they're going to be in percent. So if you make your calibration curve and your x-axis is in percent ethanol, that's perfect. Yeah, so make these solutions. You don't need to make a ton of solution, maybe 50 milliliters of each standard, okay? You're going to use like 1 or 2 milliliters per standard, so if you can use the smallest volume possible. And like I said, you're going to measure the peak height and the peak area associated with the solutions of each of these concentrations. And then you're going to measure the concentration of an unknown, okay? And that unknown you're going to make, okay? So have one of the lab partners make the unknown, and someone else can figure out the concentration. And you're going to plot, make calibration curves based on both area and height, and determine which calibration curve makes the best calibration curve, or which method makes the best calibration curve. And then you're going to run a number of samples, however many we have for you, and you're going to determine the percent ethanol in each. One of the main problems you're going to come across are interference, okay? So there are a number of things that have CO stretches, and you're going to want to pay attention to those things. Look at the labels on the things that we give you, on the samples that we give you, and see if any of the other things could be absorbing the CO stretch. Okay. So it's a relatively simple experiment. You're going to make a couple calibration curves. You're going to determine some percent of ethanol, and that's about it.